Greetings. Today we're going to talk about the ultimate law, the ideal gas law. And I guess it's not easy being green, if anybody remembers Sesame Street. All right, so here are some definitions of what ideal is. And it's a mental image, it can be in your imagination, it can be something that is in your mind is perfect, but that's not really perfect. It's just ideal. For example, I can say, my husband is the ideal husband. Is he perfect? No. But he's ideal. He's ideal for me. All right, so that's what we're going to think about when we talk about the laws. First of all, let's consider that the conditions are not changing. So if you have a problem where the conditions are changing, where you think the initial volume is X, Y, or Z, what will be the final volume? That's not an ideal gas law problem. Right there, you stop and say, this could be a Boyle's law, a Charles law, Avogadro, some other law, but it's not ideal. Here the conditions are not changing, the conditions are fixed. We are just finding out one of the variables, of the many variables that make up the ideal gas law. So the ideal gas law is PV equals nRT. And once we sing our song, you will have this down pat, because the gas laws are good to know. You can use them anywhere you go. You're talking heavy-duty chemistry. You're talking PV equals nRT. All right. Thank you, Mr. Alford, for that. All right. So what does this mean? P means pressure. V equals volume. N equals moles. T equals temperature. And R is a constant. And I'm going to show you how that constant is derived. The R constant is equal to 0.0821 atmospheres, liters, over moles, K. And I'm going to show you how that works. All right, how was this law derived? The law is derived from three laws that we have already discussed. Boyle's law, Charles' law, and Avogadro's. All of those make up the ideal gas law together. V1, P1, N2, T2 equals V2, P2, N1, T1. So putting all of that together, we derive, this is the combined gas law, and we derive the ideal gas law. So where does R come from? R is an important constant. That constant is derived from plugging in the molar volume at STP, which is 22.4 liters, the standard pressure, which is 1.0 atms, 1 mole, and the standard temperature in kelvins. This is what you get when you solve this problem, and this becomes a constant for our ideal gas law. We've already discussed what an ideal gas law, but there are some assumptions that we need to make. We say that a gas, the collisions are perfectly elastic. We have discussed that already when we talked about the kinetic theory. That there is no attraction or repulsion between the particles, and that the space the molecules occupy is insignificant. In other words, most of the space, most of the volume is empty space. The particles are so tiny that they don't really represent any volume at all. It's almost negligible, so we ignore it. It's insignificant. So under what conditions are gases ideal? Or how do they behave ideally? Well, my husband behaves ideally when I'm present, right? And hopefully when I'm not present too. But how do ideal gases behave? They behave ideally under high temperature and low pressure. High temperature, low pressure, like John Travolta. Just low pressure down here and high temperature up there. So that's how you are going to remember how gases behave most ideally. Okay, let's apply our knowledge by solving a heavy-duty ideal gas law problem. All right, so we say a sample of gas. First of all, notice that when we read this problem, read the problem carefully, there are no changes in conditions. There are not two conditions present. There's one condition, one for each variable. So I'm going to start writing it out, and I'm going to say a sample of hydrogen gas has a volume, so I'm going to write V equals 8.56 liters. At a temperature of 0 degrees. The temperature, T, equals 0 degrees Celsius, which I'm going to have to change to kelvins, which would be 273 Kelvin. And a pressure of 1.5 atms. So P equals 1.5 atms. Calculate the number of moles. So I'm looking for N, number of moles, of hydrogen present in this gas sample. And assume that the gas behaves ideally. So hint, hint, this is an ideal gas law problem. All right, one other number that I must remember is R. So I'm going to put R up here, and R is equivalent to 0.0821 atms. 0.0821 atms, liters, mole, Kelvin. So now we're going to take this number and we're going to set it up and do our problem completely. All right, so the first thing I'm going to write is my equation. PV equals nRT. What am I solving for? Well, I want to know the number of moles. So I'm looking for N. Therefore, I'm going to divide both sides by RT. Here they go away, and I'm going to have PV over RT equals N. So I'm going to plug in my numbers, 1.5 atms times my volume, which is 8.56 liters, divided by my constant, which is 0.0821, and it's atm liters over mole and K. All right, so now I have to multiply my constant times T, which is equal to 273 Ks. Now, notice it is very important that we keep the units straight. There are certain times when the problem will not be given in the correct units. You have to be consistent with the units of the R constant that you're using. And since the R constant uses atms, liters, moles, and K, all of your variables must be consistent with those units. To see if we are correct, we're going to go ahead and do the cancellations. ATM cancels ATMs. Liters cancels liters. K cancels K. We are left with moles. That's exactly what we're looking for. When we plug that into our calculator, bring it up here, if possible, I'm going to say 1.5 times 8.56 equals, divided by, parentheses, 0.0821 621 times 273 parentheses equals. My answer is 0.57287 blah, blah, blah. You don't want to use all those numbers. My least number of significant digits is 2. Therefore, it is going to be 0.57 moles. I'll put it up here, 0.57 moles. And there you have it. I'm going to give you one problem for you to solve, and I will give you the answer. There it is. We're right. Yoo-hoo! All right, so here's the next problem. Take a moment. Be sure to rewrite all of your variables. Notice, be very careful, notice that in this problem, it says what is the temperature of the gas in degrees Celsius. Does that mean you're going to solve it in degrees Celsius? No, no, no. You have to solve it in kelvins and then go back and change it to Celsius. Good luck. And the answer is 232 degrees Celsius. Hope you got it. Have a great day. See ya.